Continuing our discussion of Fourier series, today we will take up considerations of power and related aspects associated with a periodic signal. You recall that the Fourier series expansion of a periodic f of t can be put in this form in its exponential representation. To start with, let us try to calculate the RMS value of this periodic signal in terms of the Fourier coefficient Cn in its exponential representation. So we would like to calculate the RMS value of f of t. We can do this in time domain as the average of the mean square of f t, but we would like to carry out this analysis in terms of the complex coefficient Cn. Let us see how we do it. Suppose I would like to calculate f squared of t, then this can be written as Cn e to the power of j n omega naught t, n of course ranging from minus infinity to plus infinity, multiplied by the same series, but in order to facilitate our taking stock of the various terms, I would like the index here to be m instead of n. M from 1 to minus infinity to plus infinity. This of course can be written as summed on m from minus infinity to plus infinity and summation on n from minus infinity to plus infinity. So each term here gets multiplied by each one of these terms on the second summation. So I have Cn multiplied by Cm e to the power of j m plus n omega naught t. Now in order to find out the mean value of this f square t, we should find out the average of this whole series. So the average of the summation is really the summation of the averages. So we would like to find out the average of each one of these terms. If we do that, then we can sum up those averages and say that is indeed the average of f square t, because the RMS value of f of t is the square root of the mean of the square. Let us see the average value of Cn Cm e to the power of j m plus n omega naught t. What is it going to be? When we are talking about the average, we always understand that it is the average over a full cycle, a complete period of the fundamental. So this is the only time dependent term. Cn and Cm are constant. So what do we have? If m plus n is an integer, then e to the power of j k omega naught t, if you integrate over a complete period, it's going to vanish, because it is after all cos m plus n omega naught t plus j sin m plus n omega naught t. Any sine term and cosine term integrated over a complete period or an integral number of periods is going to be 0. Therefore, the average of this will be 0 if m plus n is not equal to 0. So if m plus n is some non-zero constant, an integer, that's going to be 0. On the other hand, suppose we have a case if m equals minus n, or m plus n is 0. If m plus n is 0, then this whole term becomes 1, and the average of Cn Cm is Cm itself. Therefore, the average of that would be Cm multiplied by Cm. And what is m? M equals minus n. When m plus n is 0, m equals minus n. Therefore, Cn multiplied by C minus n. And since we know that Cn and C minus n are complex conjugates of each other, you are multiplying a complex number by its conjugate. The result is simply the magnitude Cn whole square. So we have that the average of each one of these terms here will be either 0 or an expression like Cn squared. Therefore, we can now come to the conclusion that the average of f square t, the average of this term is the sum of the averages of this. Now let us see what happens. If I freeze a particular value of n and allow the m to take increments from minus infinity to plus infinity, so m goes on changing from minus infinity to plus infinity. When m takes minus n, then you have a non-zero average. For all other values of m, the contribution is 0. So when you take a particular value of m in the first summation, m equals minus n is the only term which gives some contribution, non-zero contribution. And that we do for all values of m. So the result is this will be n from minus infinity to plus infinity. For each value of n, the contribution can come only when m equals minus n, and on that condition the contribution is Cn squared. Therefore, this will be Cn magnitude squared. And what is the average of f square t? It is the RMS value of the periodic function squared, square of the RMS value, mean square value. Therefore, if I write this as f RMS, or the effective value of this one, that is equal to Cn magnitude square, n ranging from minus infinity to plus infinity. You can see this can also be written as C naught squared, or I will put it as A naught squared because I would like to put this in the terms of the coefficients of the trigonometric series. So when n equals 0, Cn equals C naught, that is A naught squared, and Cn squared and C minus n squared together are both equal to each other. Therefore, this will be 2 times Cn squared will turn out to be An squared plus Bn squared over 2, n ranging from 1 to infinity. Because An squared plus Bn squared is 4 Cn squared, because square root of An squared plus Bn squared is 2 Cn, as you recall. Therefore, An squared plus Bn squared is 4 Cn squared. 4 Cn squared upon 2 is Cn squared, and n equals k and n equals minus k together contribute. One Cn term will come for positive n, another for negative n. Together they constitute An squared plus Bn squared over 2. So what do we find? That the RMS value of a composite wave, periodic wave, the square of that equals the square of the DC term and An squared plus Bn squared, root of An squared plus Bn squared cos n omega naught t plus Pn, as you recall, is the nth harmonic. So what we have here is the peak value squared divided by 2, which means this RMS value of the nth harmonic squared. Root of An squared plus Bn squared over root 2 is the RMS value of the nth harmonic. Therefore, it is the RMS value of the nth harmonic squared. A naught squared is the DC squared. So the final conclusion is the RMS value of a periodic wave, the square of that equals the summation of or I can say the sum of the RMS value squared of the harmonic complex. Sum of squares of RMS values of harmonic components, including the DC. So that's an easy way of remembering how you can calculate the RMS value of periodic wave once you have got the Fourier series analysis for that. This of course is also equal to 1 over T naught. This is also equal in time domain 1 over T naught R square T dt over a period. So we can calculate the RMS value either in time domain or in terms of the harmonic components, whichever is convenient to you at a particular context, in a particular context. Now, let us continue this and see, as far as f of t is concerned, it could be a voltage signal, it could be a current signal. So we can calculate the RMS value for a voltage signal or a current signal using this kind of formulation. Now let us see how we calculate power when we are given two periodic signals, one being a voltage, the other a current. Let us assume that we have a network or a network element which has a periodic voltage applied across it and a periodic current IT going to the terminals. Now let the voltage V of t be V0 plus Vn cos n omega naught plus alpha n ranging from 1 to infinity. So that is the Fourier series expansion for the voltage wave, which is periodic with a fundamental frequency omega naught. This is the amplitude of the nth harmonic and this is the DC term. And likewise, let the current waveform be I naught plus n from 1 to infinity of In cosine n omega naught t plus beta n. Now the instantaneous power P of t is of course the product of V of t and I of t. And when we talk about power associated with any periodic phenomenon, we always imply the average power over a fundamental period or an integral multiple of such periods. Therefore, when we say power associated with this voltage and current, that is the power input into this network N, this is simply call this P, it is the average of the product of V of t times I of t. Always the average is over a complete period. So we take these two series and multiply them out. So you have the average of V naught plus Vn cos n omega naught t plus alpha n multiplied by I naught plus In cos n omega naught t plus beta n. Now when you look at this, you have a whole lot of terms here. But luckily for us, we are interested only in the average of these terms, the sum of these terms. So you notice that V naught gets multiplied with I naught, get multiplied with In cos omega naught t plus beta 1, I2 cos 2 omega naught t plus beta 2 and so on. But when we are talking about average, it is only this V naught I naught which results in a non-zero average. V naught multiplied by I1 cos omega naught t plus beta 1 is 0. V naught multiplied by I2 cos 2 omega 2 t plus beta 2 is 0, and so on and so forth. So as far as the V naught is concerned, the contribution to the average will come from the term V naught I naught. Similarly, when you take the fundamental here, V1 cos omega naught t plus alpha 1, that multiplied by I naught will be, you have a 0 average. V1 cos omega naught t plus alpha n multiplied by I1 cos omega naught t plus beta 1 will have an average. After all, it is a voltage and current at the same frequency. That the average will be, of course, by product of V1 and I1 divided by 2, the product of the two RMS values, times the cosine of the phase angle between alpha and beta, alpha 1 minus beta 1. All other terms, the fundamental here multiplied by the second harmonic, third harmonic, fourth harmonic will have 0 average. So consequently, P will turn out to be V naught I naught, that is the product of the DC terms. The nth harmonic terms will be Vn In divided by 2 cos alpha n minus beta n. This is the power factor associated with the nth harmonic component, n ranging from 1 to n. So this is the DC power. This is the power associated with the nth harmonic. So when you have non-periodic, when you have periodic waveforms which are non-sinusoidal, and if you make the Fourier series expansions of Vt and It, as far as the power is concerned, the average power is concerned, you can calculate the power for each frequency separately. The product of V naught and I naught is the DC power. The nth harmonic power is calculated taking the nth harmonic voltage component, nth harmonic current component, multiplying their RMS values times cosine or the phase angle difference between them. As a rule, power is a nonlinear quantity associated with the voltage and current, nonlinear function of voltages and currents. However, in the particular case where the components are of different frequencies, you can calculate, superpose the power for each component separately, as we have seen here. Normally, if you have a voltage V as the sum of V1 plus V2 and the currents I1 plus I2, you can't say V1 I1 plus V2 I2 is the power, because you can't, it doesn't work out that way. But as long as you are calculating the power associated with a pair of currents and voltage components at different frequencies, then the summation will be valid. And this is what we are having here. You can superpose power, therefore. If you calculate the power associated with each set of pair of frequency components, current and voltage, you can do that. Also, if you have the same frequency, suppose you have V, let us say Va cos omega naught t plus Vb sin omega naught t, and current, let us say, is Ia cos omega naught t and Ib sin omega naught t, then associated with this we can say power is Va Ia divided by 2 plus Vb Ib divided by 2. Here also you have some superposition principle is working out, will work out. That is because there is a 90 degrees phase difference between this component of the voltage and the other component of the voltage. Here also there is a 90 degrees difference between this current and this current. So the components associated with the cos omega naught t terms can be multiplied together, and the components associated with sin omega naught t will be multiplied together, and they can be superposed. So power can be superposed under these conditions. If we have components at the same frequency but with 90 degrees phase difference, you can superpose the two components of power, or as in this case, if you have got different frequency components, you can calculate power separately for each one of these components. That is why we can always term these quantities as the fundamental DC power, fundamental power, second harmonic power, third harmonic power, and so on, and each harmonic power can be calculated independently of the values of voltage and currents at the other harmonics. Let us take an example. Suppose I have a 10 volt signal, a voltage, an offset square wave with a period T naught, and this voltage signal is given to an RL circuit, R equals 1 ohm and L is such that omega naught L is 1 ohm. We have naturally a current I of t. The question that will be asked is, find IRMS and the power under steady state. So this is the question that has been asked. What we propose to do is, we split up the given input voltage V of t into its various harmonic components. Under the influence of each harmonic component of the voltage, we will calculate the current under steady state. So we get expressions for V of t and I of t in the form of Fourier series, and once we have them, it's easy to calculate IRMS and the overall power in the manner that we have illustrated earlier. So V of t contains a DC component. The average value of this periodic wave is 5 volts, therefore that is a DC value. And once you remove the DC value, you have the familiar square wave that we have been talking about so often in the past. So it will have a Fourier series expansion of 4 times this amplitude divided by n pi, and you have only odd harmonic terms present and sine terms only will be present, because once you remove the DC term, this will turn out to be an odd function of time. Anyway, the final Fourier series would be sine n omega naught t, and n from 1 to infinity and n odd, because this has, once you remove the DC term, this will have odd half wave symmetry. So you have V of t, and now we do the steady state analysis of the circuit, and to do that we need to find out the impedance of the circuit for different frequencies. So Z j n omega naught. So for the nth harmonic frequency, the impedance of the circuit is R plus j n omega naught L, and since R equals 1 ohm and omega naught L is 1 ohm, this is Jn, so many ohms. So we have the impedance for different frequencies, we have the voltage. So under steady conditions, under steady state, I of t will be, for each component separately we find the steady state current. If we have a DC voltage of 5 volts in a circuit consisting of R and L, the current will be V divided by R, 5, so 5 upon 1, that is 5. And the nth harmonic component, the voltage is 20 upon n pi. So the peak value of the current will be divided by this voltage divided by the value of the impedance, which is square root of 1 plus n squared, sine n omega naught t Since the impedance has an angle tan inverse of L, therefore there will be a phase difference between the current, between the voltage and the current. This will be tan inverse of arc tangent of M. So we have the complete description of the voltage and current in terms of the Fourier components. So we can calculate the whatever results that are required, I, RMS and P under steady state conditions. First of all, let us also calculate VRMS just for sake of interest. So VRMS squared will be the square of the DC term, phi squared, plus the fundamental amplitude square divided by 2, because we have to take the RMS value of the fundamental. RMS value of the fundamental is 20 upon root 2 pi squared. The third harmonic component 20 upon 3 root 2 pi whole squared, etc., etc., etc. And if you calculate this, this will turn out to be 25 200 upon pi squared times 1 plus 1 by 3 squared plus 1 by 5 squared, etc., etc. And this series is known to have a summation equal to pi squared upon 8. Therefore, this will turn out to be 25 plus 200 upon pi squared into pi squared upon 8. So this is total 50 watts. So VRMS equals 7.07, I'm sorry, 50, that is volts. A result which we would have obtained straight away from here, working out in time domain, it's quite simple. Once there is a peak value of 10 volts, you integrate this out and you get this result straight away. But it just wanted to demonstrate the use of this formula for RMS value in terms of VT. That's how we got this. We could have got this same result working out in time domain straight away. But it is not so. You could not have got this in time domain so easily for IFT, IRMS, because once you have this type of voltage, the current under steady state would have a characteristic like this. Under steady state, that will be the value how the current will vary. So you must, if you wanted to find the RMS value of the current, you would have to find out the expression for IFT in this manner, so that the starting point is equal to the same at the end of the period, to fit the initial conditions suitably, and then do the integration. But now we have got the term expression for IFT in the form of Fourier series. We can calculate IRMS in terms of its various harmonic components. So phi squared, the DC term, plus summation 20 upon root 2 n pi root of 1 minus n squared whole squared, because this is the peak amplitude. The RMS value will be obtained by dividing by root 2, and then n from 1 to infinity n odd. You calculate the first few terms, you will get 25 from the fundamental, from the DC. From the fundamental you get 10.13. For the third harmonic you get 0.23. For the fifth harmonic you get 0.03, and therefore afterwards it will be negligible. So this will be equal to 35.39, and IRMS will be 5.95 amperes. What about power? We have VFT and IFT here. So power we can calculate taking a particular term here and the associated current term here, and finding out the phase angle. So let us see the DC power P naught. Product of these two, the DC voltage and the DC component, the current, 25 watts. Fundamental power. Fundamental power, we have the amplitude of the fundamental voltage is 20 upon pi. The amplitude of the fundamental component of the current is 20 upon pi. N equals 1, square root of 2, and of course n is equal to 1. These are the product of the amplitudes. So multiplied by half, because we want to take the product of the RMS values, and cosine of the phase angle difference tan inverse of 1, that is equal to pi by 4. So cos pi by 4. And this turns out to be 10.13 watts. Similarly, P3 will be given by half of 20 upon 3 pi multiplied by 20 upon 3 pi. When n substitute n equals 3, this is root 10 cosine of whatever angle you will get for tan inverse of 3. And this will turn out to be 0.23 watts. The total power, if you assume that all other harmonic component powers are negligible, P0 plus P1 plus P3 will be 35.4 watts. So that will be total power that will be delivered by the source into the circuit. If you look at this closely, you will find that once you have got the RMS value, you could have calculated the power without going to this analysis. After all, you know the RMS value of the current in the circuit. So if you know the RMS value of the current in the circuit, the RMS value squared multiplied by resistance will be the total power in the circuit. So indeed it turns out that I RMS squared is 35.39, and the power that we got also is the same thing, 35.4 watts. But it only illustrates the procedure, the principle that is involved. That is, you can calculate the powers for different harmonic components separately and add them up to get the total power in the circuit.